Hi, in this video, I'll explain Euler's theorem in graph theory and how to use it. Specifically, I will first introduce the concept of Eulerian circuit and Eulerian path. And I will show how to use Euler's theorem to tell ahead of time whether a graph is an Eulerian circuit or Eulerian path or neither. I will also explain why Euler's theorem works so that you know where the theorem came from. Let's first review some basic terminology. In graph theory, the word graph does not mean a graph like in algebra. In graph theory, a graph means a network of points called vertices, a singular is a vertex, or nodes that may be connected by lines called edges or links. The points are the vertices, the lines between them are the edges. An example of a graph could be a diagram of cities connected by airline flights. Another example would be a diagram of actors with a link if they've been in the same movie. That's the meaning of a graph. Now, for each vertex of a graph, there's a concept of the degree of it. The degree of a vertex is defined as how many edges are at that vertex. For example, for this vertex, there are 2 edges there, so the degree of that vertex is 2. For this vertex at the bottom, there are 4 edges there, so the degree of that vertex is 4. Now go ahead and determine the degrees of all the vertices of this graph. Press pause, count all the degrees, and then come back. Welcome back. This should be your answer. Now let's talk about Eulerian graphs. It involves this game. I don't know how many of you have played this game, but when I was in elementary school, we'd play this game where one of us would draw a figure and challenge the other to trace it, but number one, without going over any edge twice, and number two, without lifting our pencil. For example, I could be giving my friend this figure, and I challenge my friend to trace it without going over any edge twice and without lifting the pencil. Go ahead and try that. Come back when you're done. Here's one possible answer. Start down here, go up here, and continuing. There we go. That's not the only solution. There are many ways of solving this. I'll show you a second solution. But before that, if you haven't tried tracing this yet, go ahead and press pause and try it now and come back when you're done. Welcome back. Here's another way of tracing without going over any edge twice and without lifting the pencil. Let's start from this other point, going down, diagonally up, continuing. And done. There are many ways of solving this. Your way is probably different from both of these as well. How about this graph? Go ahead and try it, but here's a hint. If you spend a long time on this and can't do it, just come back. Right? Press pause and try it. Welcome back. This was a trick question. We can't do this. This graph cannot be traced without going over any edge twice and without lifting your pencil. Let me show you an attempt. Let's say we try starting here and going up, sideways, down, sideways, up diagonal, and we're stuck. If we want to get to the last diagonal, we have to either retrace one of the sides or we have to lift our pencil to get to that last diagonal. That's no good. Let's back up a couple steps. Let's try again from here. going to the center here, down, sideways, stuck again. If we want to reach the last two edges, we either have to trace over one of the edges we've already done, or we have to lift the pencil. The point of this video is to show you a mathematical theorem where if you're given any graph, you can prove whether it can or cannot be traced without going over any edge twice and without lifting your pencil. The concept of what we've been doing is called an Eulerian graph, named after the mathematician Leonhard Euler, who lived in the 1700s. If a graph can be traced exactly once, no going over any edge twice, and going continuously without lifting the pencil, then it's an Eulerian graph. If it cannot be traced exactly once without lifting the pencil, then it's not an Eulerian graph. The graph on the left, we did, is Eulerian. The graph on the right, we couldn't do it, is not Eulerian. So far, so good? Now, there are actually two kinds of Eulerian graphs. The first kind is the one we've seen. We were able to go completely around and finish where we started. We call it an Eulerian circuit. For this example, we did it twice. First time we started at the bottom there, and also ended at the same point at the bottom. The second time we started on the right side and also ended there. That makes this an Eulerian circuit. The other kind of Eulerian graph is an Eulerian path. This kind we start from one vertex and we go around and we end up finishing at a different vertex. Let's take this example. Go ahead and try and trace this one without going over any edge twice and without lifting your pencil. See if your starting and ending points are the same or different. Press pause and come back when you're done. Welcome back. I'll start down here, going up, back down, sideways, up, down, and I finish at a different vertex. That makes this an Eulerian path, not circuit. So, two kinds of Eulerian graphs. An Eulerian circuit starts and ends at the same vertex. An Eulerian path starts and ends at different vertices. A common property of both the Eulerian circuit and the Eulerian path is that they both pass through each edge exactly once without lifting the pencil, but each vertex may be visited multiple times as needed. Being Eulerian is about the edges. At this time, I want to take a brief detour and introduce the man behind the concept. Leonhard Euler, 1707 to 1783. He's a genius mathematician born in Switzerland and worked in Switzerland, Prussia, Germany, and Russia. He's on a stamp in Switzerland, Germany, the old Soviet Union, the old East Germany, and the African nation of Guinea-Bissau. He's also on the money of Switzerland, and there's a meteorite named after him. There's an entire Wikipedia list of all the things that are named after Leonhard Euler. Look at the table of contents here. And check out this line. Euler discovered so many things that if they name all his discoveries after him, everything would be named Euler. It says here, in an effort to avoid naming everything after Euler, some discoveries and theorems are attributed to the first person to have proved them after Euler. In terms of this video, we're interested in Euler because he single-handedly invented the entire mathematical field of graph theory. I have a separate video where I showed that Euler's graph theory is the basis for gene sequencing, and from that, the COVID vaccine. Check it out at the link above. Euler also figured out, and that's the main topic of this video, how to tell if a graph is Eulerian, either a circuit or path, without having to trace it first. That's our Euler's theorem. With this theorem, you don't have to figure out the tracing. You just look at the graph, do some work, and know whether it is traceable. Here's what the theorem says. If the vertices in a graph all have even degrees, the graph is an Eulerian circuit. If exactly two vertices have odd degrees and the rest are all even, the graph is an Eulerian path. Exactly two odd vertices only. Not one, not three, not four, five, six, none of that. Exactly two. And what about the two vertices with odd degrees? They are the starting and ending points of the Eulerian path. Otherwise, cannot trace. No Eulerian circuits or path. So, either all even, Eulerian circuit, or exactly two odd, Eulerian path. Anything else, not Eulerian at all. Cannot trace. Just a footnote here, just to be clear, we're talking about a graph that's internally connected. We're not talking about graphs that consist of two or more separate pieces. Here's an example of an Eulerian circuit. We're given this graph. Let's count the degrees of all the vertices. Go ahead and do that. Press pause, count the degrees of all the vertices, and come back when you're done. Here are the degrees. They're all even. They're all either 2 or 4. Because all degrees are even, Euler's theorem predicts that this is an Eulerian circuit. We should be able to trace this figure without going over an edge twice and without lifting our pencil, and come back to the point where we started. Go ahead and try that. Press pause and come back when you're done. Welcome back. Here's one possible solution. Starting at this corner, I go up, down, straight down, continuing. And we end up where we started, just as Euler predicted. Let's talk about why this theorem works. Let's back up to the beginning. We start from a point, we go out from it. That means we go in the next vertex. But then, in order to continue on, we have to also leave out of that vertex. Therefore, there's an in-out pair at that vertex. At the same time, we're going in the next vertex, but we also have to go out from it. That makes another in-out pair. Every vertex must have an in and an out, and therefore the degree of a vertex must increase by 2 each time. 1 in, 1 out equals 2. If later on we go in again, we also have to go out again, so another 2. In other words, every vertex will accumulate degrees of 2, 4, 6, 8, all even numbers. Let's take a look at the bottom center vertex. First, we go in, we go out, that's an in-out pair. And the degree is 2 so far. And we keep going and going. At this time, we're back at this vertex, so another in, and back out again, another out. Makes it another in-out pair. And the degree is now 4. Because every time we go in, we must also go out. Every vertex accumulates degrees in pairs. 2, 4, 6, 8. So every vertex will be even. Make sense? Except at the beginning. At the beginning, the vertex only has out. It doesn't have in. But eventually it will. After going around everywhere, by the time we finish, because this is an Eulerian circuit, we will end up at the same vertex. So at the end, we go in that vertex, and it completes the in-out pair. Because the Eulerian circuit leaves no leftover edges, it means all vertices have in-out pairs with nothing left over. Therefore, all degrees are even. 2, 4, 6, 8, etc. Are we good? If you're unsure of something, ask in the comments section. Now let's take a look at an example of an Eulerian path, meaning it starts from one vertex and ends at another. We did this graph before. It starts from the bottom left and ends at the bottom right. According to Euler's theorem, there should be exactly 2 odd vertices. Go ahead and count the degrees and verify that there are exactly 2 odd vertices. Press pause and come back when you're done. Here are the degrees. There are exactly two odd vertices, and they are indeed the two bottom vertices where the starting and ending points are, just as predicted by Euler's theorem. Let's see why it works. Let's take a look at the starting point. It goes out and it goes around, adding an in up here, but then it ends somewhere else. It never got its in. Its degree starts with 1, adds an in out pair, goes up to 3, but never gets to an even number. Same thing with the ending point. It's got some in out pairs as the graph goes along, but in the end, it's got an in and no out. So the degree was 0, then an in out pair, got it up to 2, and in the last in, got it to 3, and never got back to even. Therefore, an Eulerian path has exactly two odd vertices, the starting point and the ending point. Let's do another example. Here's a complicated one. Is this graph Eulerian? Let's count the degrees. Press pause and do it and come back when you're done. Here are the degrees. What's the conclusion? Is this graph Eulerian? And if so, what kind is it? Press pause, think about it, and get an answer before moving on. The answer is that there are exactly two vertices with odd degrees. Two of the vertices have degree 3. The rest are 2 and 4. Because there are exactly two odd vertices, this graph is an Eulerian path, not circuit. We don't have to trace anything. We just computed the degrees, counted exactly two odd vertices, and we know this is an Eulerian path. All right, let's verify that it is. Let's find the Eulerian path. Hint, Euler's theorem tells us the two vertices with odd degrees are the starting and ending point. And it doesn't matter which is starting and which is ending. If we choose this point as starting and the other point is ending, then you go from A to B. But if you choose the other way around, you can go exactly the same route with opposite direction B to A. Just pick one of the odd vertices as starting and go from there. Go ahead and press pause and try. Come back when you're done. I pick that top odd vertex as starting. Like I said, you could start with the other odd vertex instead. Anyway, I choose that one. I go around the curvy edge, up, continuing. And I end up at the other odd vertex. Perfect. Next example. Remember this graph that we couldn't trace? Let's apply Euler's theorem to it. Check the degrees. Press pause and do it first before continuing. These are the degrees. What's the conclusion? Press pause and think about it before moving on. This graph has 4 vertices of odd degrees. Therefore, the conclusion is it's neither an Eulerian circuit nor an Eulerian path. Remember, Eulerian has to be either all even or exactly too odd. Nothing else. That's why we couldn't trace it. Let's try anyway and see why it didn't work. Suppose we start from the top left. What I'll do is I keep track of the degrees so far. With this first line, I have degree 1 at the starting point and degree 1 at the bottom. Go up. Now the bottom has degree 2 and the top has degree 1. Go sideways, the degrees 2, 2, and 2. Go down, now the starting point is full, 3 out of 3 degrees. And if I go back up the diagonal, now the top vertex is 3 out of 3 degrees. I'm stuck. I can't leave. I've used up all the degrees, all the edges of the upper right corner. There's no edge for me to continue on tracing. I don't have enough in-out pairs to go in and out of it. That's an illustration of why we can't trace this graph that has 4 odd vertices. Too many dead ends. All good? Here's a summary. When we're given a graph, a connected graph, and we're asked if it's Eulerian, first check the degrees of all the vertices. If the vertices in a graph all have even degrees, the graph is an Eulerian circuit. If two vertices have odd degrees and the rest are all even, the graph is an Eulerian path. The vertices with odd degrees, the two of them are the starting and ending points. Anything else we cannot trace. The graph is not Eulerian, no Eulerian circuits, no Eulerian paths. All right? Hope that helps. Any questions or comments, put in the comments section below. Like, share, and subscribe for more contents. And thanks for watching. Bye.